In our paper, we deal with the problem of lossy compression of motion capture data. Such data commonly consist of a sequence of values of some degrees of freedom of a skeletal structure. Euler angles are usually used. A common problem with lossy compression of such data is that a precision loss in different degrees of freedom has a vastly different influence onto the overall distortion. In particular, loss of precision in bones that are located near the root of the skeletal structure influences the whole set of child nodes, and it is easily perceivable. The same amount of precision loss in the extremities may be hardly perceivable at all. The problem is even more pronounced with more complex skeletons, where the superfluous precision used for extremities strongly adversely influences the overall data rates in compression. A common approach to this problem is to encode the local coordinate systems independently of each other. In order to do that, 3 so-called virtual markers are used for each bone of the skeletal structure. This of course leads to an increase in data redundancy, which has to be counteracted in the subsequent compression. Moreover, the resulting motion capture data might be incompatible with the original data in terms of bone lengths. To fix this problem, methods of inverse kinematics are sometimes employed at the decoder side, making the decompression slow and inefficient. Our approach avoids this problem by using a different pre-multiplication constant for each of the degrees of freedom. The method takes into account the structure of the skeletal hierarchy, the lengths of the bones, and the poses that are contained in the input data. We derive a closed-form formula for the pre-multiplication constants, and our approach also allows optimization with respect to various error measures. After the suggested pre-processing of the degrees of freedom, we propose using a simple lossy compression approach based on principal component analysis. We apply the PCA twice, first to reduce the dimensionality of the space of poses, and then to exploit the correlations between the degrees of freedom. The performance of a motion compression algorithm strongly depends on the metric being used for distortion evaluation. Researchers have previously found mean squared error inadequate for measuring perceived distortion. However, only little effort has been invested into seeking a new measure that captures the perception better. We propose a novel evaluation method building on the concepts used in dynamic mesh compression. As can be seen from the video, it matches the distortion perception much better than mean squared error, and it can be used as an optimization criterion in compression. Our proposed approach is easy to implement and fast to execute. Together with the proposed pre-multiplication, we are able to reduce the required data rates by about 50%, while introducing the same amount of distortion compared with the state-of-the-art methods such as the repeated motion analysis.